This is part 2 of the lecture on oscillations. This lecture is specific to Conceptual Physics AB. In this lecture, we're just going to take a look at an example, and I'll demonstrate the example for us. Please copy it down into your notes as I read it here. Okay, a mass of 100 grams, is attached to a spring with a spring constant K equal to 10 newtons per meter. The mass oscillates on a horizontal frictionless surface. I'll demonstrate this vertically, but for now, let's begin to draw out the problem in the following way. Okay, so here is our oscillator oscillating about the equilibrium position like so on a horizontal frictionless surface, and then we're given the following. First of all, the mass is 100 grams. Okay, I'm going to go ahead and convert this into kilograms. So I multiply by 1 kilogram per 1,000 grams. Grams cancels, do the math here, and it ends up being 0.1 kilograms. Okay, and then the stiffness of the spring constant itself, is given to us as 10 newtons per meter. Okay, in part A of the problem, we're just going to calculate the period of the oscillation. So the period of the oscillation, capital T, is described by the following expression, which was introduced in the previous video. So let's just go ahead and directly calculate this, and we'll get a time in terms of seconds. Okay, so 2 times pi, and then multiplied by the square root of the following. 0.1 kilograms divided by 10 newtons per meter. You take the square root of the whole thing underneath the radical sign, and this then equals about 0.63 seconds. And then in part B of the problem, we're asked to calculate the frequency. So the frequency is equal to the inverse of the period. The frequency, by the way, is also referred to as the natural frequency. And then therefore, the natural frequency of the spring is given to us as 1.6 hertz. Like so. So then therefore 1.6 oscillations take place per second with this mass attached to this particular spring. Okay, and then briefly in part C of the problem, we're going to see what happens with these values when we attach an additional mass of 50 grams to the object. Okay, so let me call this part C now. What we're doing is we're taking the mass of 100 grams and we're adding 50 grams to it. So the mass is 150 grams. That is equal to 0.15 kilograms. It's the same spring as before. The spring constant K is 10 newtons per meter. So let's just go ahead and quickly recalculate the period and the frequency. Okay, so using the formula for the period, first of all, I have 2 times pi, and then multiplied by the square root of the following. 0.15 divided by 10, take the square root of the whole thing, then it ends up being about 0.77 seconds. So notice that with the additional mass, this then means that the period is larger. The greater the mass, the greater the period. The frequency, which is once again the inverse of the period, so take the reciprocal or the inverse, that comes out to be about 1.3 hertz. So with this particular period, the frequency ends up being this value. If the period is longer, as it is here in part C, as opposed to earlier in the problem, this then means that the frequency is smaller. Let me go ahead and demonstrate this now by using my demonstration spring. So I'm going to go ahead and tilt my phone. That is like so. Okay, now I have a relatively small amount of mass here attached to my spring, and then I set it into oscillation like so. Relatively short period, and then therefore high frequency. I'll detach this mass. Now here's part C of the problem. I attach this greater mass like so, set it into oscillation, and you can see that the period is longer, and then therefore the frequency is smaller.